Section 19.4, equipotential surfaces and their relation to the electric field. So what is an equipotential surface? It's a surface on which the electric potential is the same everywhere along that shape that you can trace out. So for instance, if our electric potential of a point charge we just found is kq over r, and that means the potential will be the same as long as the r is the same, as long as the radius stays the same. So if we have a point charge positive q here, you can create these spherical shells all around the point charge where anywhere on the shell you're going to have the same potential electric potential value. Now, interestingly, the electric force does no work on a charge as it moves on an equipotential surface, right? So if we're at point A and we travel along this shell that's at a constant r from the charge, we're not doing any work because we're just at a constant distance from the charge. So we're just at this equipotential. The electric potential is not changing, so the work has to be zero. If we instead go from A to D, now we're changing between two different equipotential surfaces, and we've changed the radius. So that change in radius is what's going to influence the change in work. It's going to require work to be able to change that radius. Now, the electric field created by any charge or group of charges is everywhere perpendicular to the associated equipotential surfaces and points in the direction of decreasing potential. So with our positive point charge, if we draw in our equipotential spherical shell surfaces here, we could draw the electric field as going perpendicularly through these shells and pointing towards lower potential, so pointing away from the positive charge. So this looks much like our electric field lines before, of going out of the positive charge and towards the negative charge. The only difference is now we're also adding in that it is piercing the equipotential surfaces or lines. If you want a two-dimensional view of this with a negative charge added in, we have one right here. So this is just a cross section where these blue lines should be a full spherical shell, but we're just looking at one cross section of it. And so anywhere on the circle, it's going to be a constant potential. The potential has one value, right? And as you move further and further out, the circle gets spread further and further. But now we also have a negative charge over here, and that has equipotential line circles around it, where anywhere on that the electric potential is a constant value. Like it could be 4 volts anywhere on one of these circles. Another circle might be 5 volts. Great. And then the red lines are our electric field lines. Just as we saw in the last chapter, the electric field lines go from the positive charge to the negative charge. But now we see why they have kind of that weird arching shape, where they don't just travel in a straight line, except for in the very middle, from the positive to the negative charge, because these electric field lines need to have a perpendicular intersection on the equipotential surfaces. So that means they're going to go up first, and then they can start to bend over and only go horizontal at the very midpoint, and then they start bending down and curving down there. So that's what the equipotential surfaces and the electric field lines look like for a positive and negative charge, which is also known as a dipole when you have a single positive and negative charge. What about if we have a parallel plate capacitor, right? 2 plates with opposite charge. Well, if you have 2 plates with opposite charge, one of them is positive, one of them is negative, then the equipotential surfaces are anywhere where you're at an equal distance from one of the plates. So their equipotential surfaces are parallel to the plates themselves, and the electric field, just as we've previously seen, points from the positive plate, the higher potential, to the negative plate, the lower potential, which is a perpendicular intersection of the equipotential surfaces. Note we also have another way we can calculate the electric field here, and that's that with this parallel plate capacitor, we can get the electric field if we know the electric potential difference, and we divide it by the distance between those plates with a negative sign. That will also give us the electric field. Right. So let's look at this example. The electric field and potential are related. The plates of the capacitor are separated by a distance of 0.032 meters, and the potential difference between them is VB minus VA is negative 64 volts. Between the two equipotential surfaces shown in color, there is a potential difference of negative 3 volts. Find the spacing between the two colored surfaces. So we're trying to figure out, okay, we know the total spacing, delta S, is this 0.032, but what about this much closer spacing between the two plates here? What is that? Well, the key here is that even though the potential difference is going to be different depending on where you are, we know that it goes from being negative 64 over the entire difference and only negative 3 between these two plates, the electric field is uniform on the inside. So we're going to take advantage of that in solving this problem. So if we take that the electric field is negative, the change in potential divided by delta S, and the change in potential is the negative 64, so that the negative there cancels. Sorry, I lost the negative there. And so it comes out to positive 2.0 times 10 to the third volts per meter. This is another unit that you can use for electric field. Previously, we saw it as newtons per coulomb, but volts per meter also works. It's the electric potential divided by the distance. Now, if we know that, we can now rearrange this equation using the same electric field, but a different change in potential. And we'll solve for delta S. So multiply the delta S up and divide by the electric field. We get that delta S is equal to negative the change in potential divided by the electric field. And the electric field is the same anywhere between the plates. That's why we can use this 2.0 times 10 to the third volts per meter. The potential difference up here is negative 3.0 volts. So the negatives once again cancel, and we're left with a separation of 1.5 times 10 to the minus third meters. We can do a quick check. This is indeed much less than our total plate separation of 0.032 meters, because this is now, if we move it over 3 decimal places, this would be 0.0015 meters. So this is not just half as much, but a tenth, half of a tenth of as much. So very, very small. So this introduces the idea of equipotential surfaces and how it's closely related to the electric field. We have a convenient equation here that allows us to approach the relationship between the electric field and the electric potential. That concludes this section. We'll take a closer look at capacitors, these parallel plate capacitors, in the very next section. So stick around.